So we've got a certain wire has a diameter. Tell me. So the people on the recording know what we're talking about. This is page 279, number 1. So a certain wire has a diameter of 0.079 millimeters, a resistance of 10 ohms. Determine the resistance when the diameter is increased. So we've got our initial resistance right here. We're asked to determine the resistance. So we're looking for the new resistance. Our current diameter is 0.079. Now diameter, remember, it's not the diameter that changes, it's the area that changes. It's also an inverse, so the diameter has to be squared. It's also an inverse relationship, which means the diameter of this wire goes on bottom. So then our new diameter is going to go up here, which is 0.254. So we're just going to punch this in as 10 times 0.079 squared divided by 0.254 squared should give us 0.967. Okay. So that'll do it. Okay, yeah. The basically like number 2 to make sure you change the 0.102 millimeters to 102 micrometers or whatever. Make sure everything's in the same units. Yep. Then for 81, on page 281, the biggest thing is always make sure the length is in meters, the diameter is in millimeters. As long as you're doing that your length is in meters and your diameter is in millimeters, you can drop the times 10 to the negative 6 from the resistivity. Because that's since we're doing our area in square millimeters instead of square meters, the conversion between square millimeters and square meters is 10 to the negative 6. So that actually cancels that out. So like number 1, determine the resistance. So we're asked to determine the resistance. So the form of that equation that is resistance is R is equal to resistivity times length divided by area. We're just taking that rho equals RA over L formula and rearranging it. So determine the resistance of 15 meters of wire. So that's our length, 15 meters. Has a diameter of 2.588. So the area is pi times 2.588 squared, and then of course divided by 4. And it is aluminum wire. Aluminum wire is 0.0283. So 0.0283 times 15 divided by, now I got to put this in parentheses for my calculator, 3.14 times 2.588 squared divided by 4. Close the parentheses. I get 0.0807 ohms. Which for 15 meters of wire, that sounds about right. Let's jump down to, so the number 2 is the same. We're just using nichrome instead of aluminum and whatever. Number 3, we're asked to find the length. So now length, if we rearrange the formula, length is equal to resistance times area divided by the resistivity. I'm just taking this formula, multiplying by A and dividing by rho. So determine the length, 24 gauge, so that's going to give me the area. Let's find the resistance. Resistance is 0.85 ohms. So now my area is going to be pi, so 3.14 times 24 gauge. So we flip back. Page 277, 24 gauge is 0.511. So 0.511 squared and then over 4. That has to be divided by the resistivity tungsten 0.0552. So we punch this in 0.85 times 3.14 times 0.511 squared divided by 4, then divided by 0.0552. So I get 3.16 meters. Which makes sense. Tungsten wire has a pretty high resistivity, so yeah, it only takes a short piece. Number 4 then is going to work the same way. Number 5, determine the resistivity. So resistivity is equal to RA over L of an unknown metal conductor that is 10 meters long. So 10 goes in for L. Diameter, let's see, the resistance is 1.61, so I'm going to put that in here. Times my diameter, so I'm going to put my area as 3.14 times that diameter of 0.643 squared, and then that's over 4. So 1.61 times 3.14 times 0.643 squared divided by 4, then divided by 10 meters, 0.0523. So if we look at the table, does that match up with any of them? It really doesn't. It's probably closest to tungsten. It didn't ask us to determine what conductor it was. It's just the resistivity. But that would be how you would determine if you have an unknown wire and you want to determine it. You would do that test, do a resistance test. Now the resistivity usually will show up being slightly higher than what it really is. So if you test something, it gives you a resistivity of 0.0199 or whatever. That's most likely copper, but there's the insertion loss when you hook up your meters on the ends and whatever. Does that make more sense? Okay. Well, I want to briefly go over that packet on binary numbers. I think what we'll do is today we'll talk about converting numbers, and then tomorrow we'll talk a little bit more about converting numbers and then operations with numbers, which is going to put us, unfortunately, with Wednesday as our test. It all depends on how everybody's doing with this binary stuff. We'll take more time if we have to. Yes, it will. There'll be some of them on there. So then let's take a peek here. We're going to have, let's just look at number systems in general, first of all. Our number system is called a decimal number system. What decimal means is base 10. Deci is 10. So what that means is our place values in our number system, actually place values in any number system, are exponents. And in our number system, the base of that exponent is 10. The ones place is 10 to the 0, because anything to the power of 0 is 1. Tens place is 10 to the 1. 100s is 10 squared. Thousands is 10 third, 10 to the 4th, 10 to the 5th, and so on. The tenths is 10 to the negative 1 is 1/10, 10 to the negative 2 is 1/100th, and so on. We're not going to deal so much with the decimals, but we are going to deal with everything in front of the decimal point. This is base 10. So if we want to look at a different number base, well, let's do this. So let's say we got 2,384. That is 2 times 10 to the third plus 3 times 10 to the second plus 8 times 10 to the 1, or just 10, plus 4 times 10 to the 0. That's what those values literally are. So that's the positioning in that place valued system. There's something called an octal number system, which is base 8. So let's take a look at how that would look. This is going to be 8 to the 0, which is 1. This is going to be 8 to the 1, which is just 8. This will be 8 squared, which is 64. 8 to the third, which is going to be 512. 8 to the fourth, which is 4,096. 8 to the fifth, which is going to be 32,000. I've got to cheat. 768. And of course, it would keep going. Notice those are slightly smaller. 10 to the fifth is 100,000. 8 to the fifth is only 32,000. Those are the place values. So if I put in, now first of all, in our base 10 system, what's the largest digit we can have? 9. Very good. 1 less than our base. So in a base 8, the largest digit we can have would be, you got it. So we could not have any digits bigger than 7, because at 8, that's like having a 10. You would have to carry to the next spot. So if we have something like 2836. Notice I was very careful not to say 2,836, because those digits don't mean that. That 2 is 2 512s. So it's 1,024. I screwed up and put an 8 in there, didn't I? That can't be an 8. That can only be a 7. That 7 is in the 64s place. So 7 times 64 is 448, I believe. The 3 is in the 8's place, so 3 times 8 is 24. And then there's 6 in the 1's place. So the value of that, if I want to convert it into base 10, add them up. So that is 1,502 in base 10. So the notation we would use, put a little 8 there so that's base 8, is equal to 1,502 in base 10. This is still base 8. Those are the 1s, 8s, 64s. 1, 0, what does that stand for? Yeah, 1 times 8 is 8, and then there's 0, so it's just an 8. So 1, 0 in base 8 is 8. So 352, well, again, that's 3 times, what place value is that? For the 8s, this is base 8 still. Sure. 8 squared, so 64. It's 182. The 5 is going to be times 8, so that's 40. And then 2 is times 1, so it's just 2. So it's 234 base 10. So 352 base 8 is 234 base 10. It's more difficult to convert the other way. Once you have the base 8, I mean, all you're doing is multiplying the place values to convert it into base 10. But if I have a base 10 number that I need to convert into base 8, yes, it's division and remainder. So let's say I'm going to throw out here the number 15,200. Now the next place value here was 32,000, so I don't need to go up that high because 15,000 isn't going to go up that high. So we start out with the first place value that's smaller than it, which would be the 4,000. So if I take 15,200 and I divide by 4,096, there you go. You get 3, yep. I'm just going to punch it in so I can show you how to keep it in the calculator here. So you got 3.7, so it is 3. So 3 goes here. Now we got to figure out how much is left over. If I subtract the 3 and multiply back by the 4,096, gives me a remainder of 2912. Or you could have taken the 4,096 times 3 and subtracted it from the 15,200. Either way. We're left with 2912 at this point. Again, we could have done, this is going to be minus 3 times 4,096. 512 goes into that. You said 5 times? Perfect. So that's 5 there. So if I'm subtracting that out, 5 times 512 is 2560, right? So that leaves us with 352. Divide by 64, you got it. That's going to be 5 again. 5 times 64 is 320, right? So you got 32 left over, exactly. 32 divided by 8 is my next digit. Is 4. So there's no ones, that's got to be a 0, yes. So this is 35540. I shouldn't even put in the comma because it's not really appropriate. So 15,200 base 10 is 35540 in base 8. Actually, let's do this. Hexadecimal is base 16. So that means my place values, this is 16 to the 0 or 1s. 16 to the 1 or just 16. 16 squared is 256. 16 to the 3rd should be 4,096 again, yep. 16 to the 4th, we'll stop there because it's going to get really large. 65,536, perfect. So obviously the largest digit we can have here would be what? Is a 15. Well, we don't go above 9 in our number system. So what happens is, of course, 9 is just a 9. 10 is represented by the letter A. 11 is the letter B. 12 is the letter C. 13 is D. 14 is E. And 15 is the letter F. So it is possible in hexadecimal numbers to have FAD7 as a number. So the F, of course, is 15 times 4,096, which is 61,440, okay. The A then is 10, so that's 10 times 256, which will be 2,560. The D is 13 times 16, which would be what, 208? And then 7 times 1 is 7. So that adds up to give us 64,215 in base 10. So FAD7 in base 16 equals 64,215 in base 10. Now again, going the other direction is a little more difficult. If we have base 10 and we want to get to hexadecimal, I'm just going to take this with me because we need it. So let's say we have let's see here. We go 52,803 in base 10. And I want to convert it into hex. Perfect. We're going to start out dividing by the 4,096. So 12. So 12 is the letter C. So 4,096 times 12 subtracted back out, what does that leave us with? 3,651. So now the next one is the 256. So it's 14, which is D, right? No, E. E is 14. So then we do okay, something went wrong there. So 36, let's just do it the hard way. 3651 minus 256 times 14. It really probably should be just 67. Yeah. So 67 is left. We're going to divide that by 16 is our next place, which is just 4. What's that? Yeah, 4.75. So then there's 3 left over, right? So that 3 ones. So CE43. So 52,803 is CE43 in hexadecimal. Binary is, of course, base 2, which means the largest digit is 1. It's used in electronics because it's either a 1 or a 0, on or off. So then our place values well, in a byte, there are 8 bits. So you've got 2 to the 0, which is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3rd is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. 2 to the 7th is 128. And it can keep going. But yeah, if you have certain games you play, like Madden 2003, I don't know any versions after that. That's the only one I've actually broken down and done the math on. If you score, I want to say it's 256 points, it'll actually stop at 253 because it only allots 1 byte for scoring. So if these are all ones, 255 is as high as it can go. So it'd stop your score at 255. your total offense, you'll stop at 1,023, which is going to be taking you up to 2 to the 9th. It only allows 10 bits for score, so it'll cut you off at not for score, for yardage. So it'll cut you off at 1,023 yards. So you can't get 1,024 without even a 10th bit. Actually, 11th bit would be 1,024. 10 bits would be 1,023. So our digits are ones or zeros here. So looking at that, this number 10111011, it's really easy. Well, what's 1 times 64? 64. 0, we don't need to use that one. 1 times 16, 16. 1 times 8 is 8. Don't need to put in the 0. 1 times 2 is 2. 1 times 1 is 1. What's that? 91 total. You got it. So let's look at this one. So this is 1, 2, 4, 8, 16, 32, 64, 128. So yeah, it's 128 plus 64 plus 32 plus 4 plus 2. $230? Going the other way. Now again, we can't use really large numbers, so I'm just going to do 211. So I could go through the process of dividing by 128, but how would I just subtract 128? I'm going to actually write this a little different. I can take 128 out. I know I can only take it out once. So that's 1 in the 128. Leaves me with, what? 83. Can I take out a 64? So that leaves me with a 1 in the 64, and I subtract 64. It leaves me with 19. Can I take out a 32? No. Can I take out a 16? Yes. So I put a 1 in the 16, leaves me with a 3. Can I take out an 8? Nope. A 4? No. A 2? Yep. So 3 minus 2 is 1. Leaves me with 1. Oops, I don't. 2 is 1. So there it is, 11010011. The reason octal and hexadecimal mix or exist is because of their relationship to binary numbers. There's really no use of octal or hexadecimal numbers other than to compact binary numbers. So of course in binary, 0 is 0. 1 is 1. 1, 0 is 2. 1, 1 is 3. 1, 0, 0 is 4. 1, 0, 1 is 5. 1, 1, 0 is 6. 1, 1, 1 is 7. What I can do is simply this. Notice 7 is the largest digit in the octal number system. So what I can do is this. There's a string of binary digits. Notice the most this takes is 3 digits here. So what I'm going to do is I'm going to fill in zeros here to complete those to 3 digits each. I can start at the end of this number and go 3 digits at a time. Happened to work out. It didn't have to work out that way. I just add zeros at the beginning to make it come out. 101 is a 5. 111 is a 7. 010 is a 2. 100 is a 4. And 101 is a 5. So this is binary. This is its octal equivalent. So the conversion from binary to octal is very, very simple. Going the other direction is just as simple. Let's say we have 7132 in octal, and I want to convert it to binary. Well, a 2 is 0, 1, 0. 3, 0, 1, 1. 1, 0, 0, 1. And 7 is 1, 1, 1. So I just converted my octal into binary. It's just that quick. Hexadecimal involves just taking 4 digits into 1. And what I'll do is we'll go over that tomorrow. I think I've done enough for you today. I'm pretty sure I'm going to have to catch everybody else up tomorrow. So, in that packet, put this one away. You can look at it's page 503 through 504. That's just converting. They do get into decimals. Now, if I'm dealing with binary, this is the 1s, the 2s, the 4s, and the 8s. Well, this is the 1/2. This is the 1/4, the 1/8. So, 0.5, 0.25, 0.125, and so on. So it's really not that much more difficult, no. So you just got to subtract them off as you go through the place values if you're going from base 10 into binary. And we'll go over those a little bit more tomorrow. Also, let's see what they've got up here. Don't want you to deal with operations with binary. Page 511. So converting from octal and binary to octal. On page 515, do the conversions on the beginning of that one as well. And like I said, I fully expect to have to spend quite a bit of time tomorrow. We may not get to the test till Thursday. It all depends on how it goes. Well, just do the odds. Yep. And like I said, if you hit something that just doesn't look familiar, just don't sit there and beat your head against the wall over it. We'll be spending more time on these.